So this week, we've got 7.7 and 7.8 we're going to talk about today. We're going to do a little bit of stuff from chapter 8 on right triangle trig on Thursday in class, and I'll have the lessons and homework up related to that a little bit later today. But in any case, as promised last week, today what I've got for us, we're going to talk a little bit about the tangent function and how that's related to anything else, including our circles, but not worrying too much about, it doesn't have the sort of details like amplitude and midlines and things like that your sine and cosine curves do. So we're just going to generally talk about when it's defined, when it's not, and what it means. And so it'll be a fairly brief lesson on section 7.8, but I did want to get some additional practice at dealing with sine and cosine curves and functions and interpreting all the pieces about them, like the period and the amplitude and things like that. So because it's kind of helpful to be able to draw on stuff, I have a worksheet for us today. I'm going to pull up a copy of it up here too. But we're going to go through this together instead of just having a computerized version, although I will post this into Canvas so you can download an extra copy of it later if you wish. But there's two sides to this. One side that has a few graphs on it that you can write equations for either as sine or cosine functions. Sine and cosine are basically the same shape, just shifted around a bit. There's probably one that's easier than the others, but the backside then is an application about Ferris wheels with a whole bunch of different questions. It's kind of a variation on a few of the questions from the 7.7 investigation. But just so you can like draw things out together, I just thought I'd put together a worksheet for this. Graphs are kind of easier to do manually, like measure things and point out pieces than they are on computers and staring at screens, I think. Maybe that's just me, but in any case, let me pull up a copy of this. Where did I put it? What format was it? I don't remember. This one. Yeah, so in any case, I know those axis marks are a little bit hard to see, but in that question 1, the ones that are marked are pi over 3 and 2 pi over 3, or I guess, yeah, that is question 1. And in question 2, those are 5 pi over 4 and 5 pi over 2, which is the same as 10 pi over 4. And in question 3, those are pi over 2 and pi, positive and negative that you see. And in question 4, it's pi and 2 pi. Those came out a little bit light on the photocopy for whatever reason. But in any case, take a look at these. I know you've been working on this. This is part of 7.7. We've talked about some aspects of this, but I want to give you a chance to kind of try to figure out what you can with those 4 graphs. And if you're quick at that, go ahead and take a look at the other side too. But this is our first order of business today. Make sure we've got kind of some ways to think about how to piece together a function based on a graph, which also could have been just described instead of an actual graph. And then we'll do another application example. Try to see what you can figure out about those graphs. Having had a bit of practice with this so far, and an assignment that covers this due later tonight. Covers other things also, but this is one of the things. All right, let's take a look at these graphs. So if I just wrote like standard sine or cosine, just like y equals cosine of theta, or x, or whatever letter you want. Y equals sine of x. I'm going to use theta. Whatever letter you want as the input variable, or f of x, f of theta, g of theta, whatever notation you want to use. If we just have these basic no extra numbers sorts of equations, what is the value of the amplitude for either of those two? Yeah. Yeah, it's just one. And by amplitude, again, that talks about how far above or below the midline the curve goes. So thinking about rotation around a circle, if we're measuring the y unit or the output in radius lengths, rotation around the circle, your distance, that radius is always one radius length. And so you're going to go between 0, well, if you're on a sine curve, 0 to 1 to 0 down to -1 radius length, regardless of what your radius is. If you have a larger circle and you're not measuring in radius lengths, if you're measuring in inches or meters or feet or whatever, then in order to account for that, the fact that you're scaling up the size of your circle and not just concerned about how many radius lengths, but how many inches or something like that, you need to have a coefficient on these, multiplies the whole function by a certain value, or in terms of order of operations, that multiplier would be like a last step. If I just put it in like y equals 3 sine of theta, would have y values that are 3 times as large as, either more positive or more negative, 3 times whatever the y values would be without. So zeros stay 0, but everything else gets farther from 0 by a factor of 3 if you put a coefficient on there. Now without a written coefficient, that means it's 1. And so our amplitude, the maximum and minimum values, are 1 unit away in that case. So on these 4 graphs, let's see, 1 and 2, they don't have amplitudes of 1. Looking at questions 1 and 2 that I have on the screen right now, what is the amplitude of question number 1's curve? If you can see that on your paper, I know they're small numbers. What is it? 4. What about number 2? It's 2, right? So amplitude equals, what is it, 4? Amplitude is 2. All right, so I'm gonna do the other 2 in a minute. The next question asks us about the midline. Now, 3 out of 4 of the questions on here aren't very interesting. The midline is the horizontal line that's halfway between the maximum and the minimum values that the curve reaches. So for standard y equals sine of theta, y equals cosine of theta curves, that midline is just the x-axis. It goes equally above and below that. In other words, it hasn't been shifted anywhere, and we're measuring, thinking rotation around a circle relative to the center of the circle. So the midline on all of those is the horizontal line, that's the x-axis, that's y equals 0. And it is in these questions 1 and 2 also. These go equally above and below the x-axis, so the horizontal line y equals 0. Oops, right, midline, y equals 0. Midline, y equals 0. All right, so period for typical sine and cosine curves, y equals sine of theta, y equals cosine of theta. If we're thinking about, again, kind of a basis for describing these rotation around a circle, that input is an angle in radians, then the period is going to be how much until it starts repeating itself? Like how long, how many radians do we have to pass through before the values all start to repeat themselves in the same sequence? 2 pi. 2 pi, all right? So y equals sine of theta, y equals cosine of theta, those both have periods of 2 pi radians. So if we were measuring our angles in degrees, then that would be 360 degrees. But typically when we write these functions like this, it's most standard that we're talking about radians. That way we can refer to these in terms of radius lengths. They correspond more easily. There's no like translation between degree measurement and number of radius lengths that you'd have to do. So, for instance, this first function here, looking at these examples, there's a point at the origin, and it goes up and down and back up to the origin in a way that if I were to continue on from there, it would continue the path just like was happening at the origin and just like that's happening back here, going upward through the origin. So the beginning and the end of this cycle, or the beginning of one cycle and the beginning of the next cycle, you can see because one starts at 0, it's easy to count if you can find a point at 0 and a corresponding point at 2 pi over 3. That seems to be the beginning of the next cycle. I mean, we can't actually see it, but we'll assume that it continues on in the same pattern. That would mean that the period for this first one is 2 pi over 3. So, is that longer or shorter than 2 pi? Is 2 pi over 3 more or less than 2 pi? Yeah, it's less, right? It's a third the size. We've divided the period by a factor of 3. So we talked about this in a different order. I think last Thursday. It could have been the end of class on Tuesday also. Talked about period for a while. But the fact that it goes in this graph through its full cycle of values between 0 and 2 pi over 3 doesn't mean that we've violated a circle. What it means is that the angle that we're going through these angles more quickly than the input of the function is. Or in other words, there's other stuff in here besides just an angle that's putting in an angle of 2 pi over 3 make the function think you've put in 2 pi and are ready to start your next circle. And what that must be then, this is going faster through all of its values, or it finishes in 1/3 the time. A way to think of that that is maybe helpful, it goes through this cycle in 1/3 the time, so it's going through angles 3 times as fast, or it's taking the angle, whatever angle input we have, and multiplying it by 3, tripling it, so that the function input isn't just the angle, it's an angle multiplied by 3, which is why putting in an angle of 2 pi over 3 results in a value that seems like it wouldn't happen until 2 pi, because we do this trick of multiplying by 3. Or, let's see, I'll write the angle. The angle is multiplied by 3 in order to cut the period length by a factor of 3, divided by a factor of 3. So this is shorter because we do something to the angle before we find the sine or cosine of it. Or in other words, if I wanted to write a function that models this looks most like a sine function. Sine models the vertical position as we rotate around a circle counterclockwise, starting from this like positive x-axis direction. So angles in standard position starts with a vertical position of 0, goes up to 1 by a quarter of the way through the period, quarter of the way through a rotation, down to 0 by halfway, -1, and then back to 0 by the time we've done a full rotation. So that's the pattern of a sine function with just some alterations made to it. So if I wanted to write a function for this, whether I call it f of theta or y equals, you know, whatever I want to call it, let me call it f of theta. A sine function would be easiest to use, but it can't just be sine of theta, otherwise it would take to 2 pi to start repeating. It must be of something 3 times as big as whatever theta I substitute in. Or this is sped up by a factor of 3. Or it's a horizontal compression by a factor of 3, however you want to think of that, to make the period 2 pi over 3 instead of 2 pi. You can think of this as squishing it together left to right. You can think of it making it go through angles faster because my angles get tripled. But the other thing that I need on here is to account for the fact that this isn't like a standard sine function. Midline of 0, that's same as usual. Period of 2 pi over 3, this would make that happen because substituting in like theta equals 2 pi over 3 would make this come out to be a sine of 2 pi. All right, so subbing in 2 pi over 3, the function thinks it's a 2 pi. But in order to get an amplitude of 4, I need to stretch this out vertically by a factor of 4. So 4 sine of 3 theta, if I were to graph y equals that, or you know whatever function name you want to call it, would look like this graph here. Now, there are also infinitely many other graphs that would look the same, and that sounds weird. But because of the symmetry, like this left to right translational symmetry, both for sine or cosine, I could even write this in terms of a cosine function if I wanted to. Like for instance, like I can say, well, maybe you know, it's shifted backwards by 2 pi over 3. Okay, that's weird, but I can do that. The shifting left and right is a little bit tricky when you've also got a speed thing in here, but we don't really need to shift this one to answer it, so let's do it the easy way, sine curve. So what about that number 2 there? What's the amplitude on number 2? What's the maximum distance away from the midline? 2. Okay, so we've still got a midline of 0. We've got an amplitude of 2. What about the period on this one? Yeah, 5 pi over 2. It's a little bit messy. So 5 pi over 2. Is that bigger or smaller than 2 pi? Bigger. It's 2.5 pi, right? Like 5 halves pi. So it's spread out a little bit. Or in other words, if I go to write it this way, this one was squished together, and I have this number larger than 1 here. This one's spread out a little bit, so I should have a number smaller than 1 there. So there is a formula that you've probably seen mentioned, and it's just this: how do you convert between that speed factor, like how fast it goes through its cycles compared to regular, versus what the period is. And let me just write that on the board. Sometimes it's more helpful than others. When you have weird, like I can just say, oh, this is almost 2 pi, it's just been divided by 3. So I'll triple my angle and that makes up for it. Well, this is multiplied by 2.5. So, well, I'm going to divide by 2.5. Or actually, it's not multiplied by 2.5, it's 2.5 instead of 2, which is a factor of like, what, 5 to 4? So I'm going to multiply by 4/5, which is maybe a weird, like, I know it should be something with some number smaller than 1 in that spot. And we'll use a sine curve. You could also use a cosine curve. But there should be something smaller than 1. But the relationship between that coefficient and the period of a function has to do with this, how big it is compared to 2 pi. So usually the letter that's used for the number in this spot as a generic thing is b. I don't know how they end up with b there. There's so many different places you could have letters. But let me say that I'm talking about sine or cosine of b times theta. Whatever that b is, 2 pi over b is equivalent to the period of that function. So like in this one, I had a 3 here. 2 pi over 3 was the period of that function. Now, this is like a fractional equation. You can solve for either one of those. It might be easier to look at, like if I'm writing the main period there, it might be easier to write it over 1. But lots of times the period is a fraction anyway. In a fraction equal to fraction situation, you can cross multiply to solve either for this one or for that one. So, for instance, in this one, the period was 5 pi over 2. I'm going to write 5 pi over 2. I don't have to write 5 pi over 2 over 1. But this, if I solve this proportion for b, I'm going to know what number to stick in either of those two spots. If I had 5 pi over 2 as the period of a sine or cosine function, I can solve this equation for b to figure out what that coefficient is supposed to be. You should know the sign of it, the size of it, based on how big it is relative to 2 pi. If you have something less than 2 pi, you should have a larger than 1 number. If you have something greater than 2 pi as the period, you should have something as a less than 1 number here. So you can kind of check to see whether it makes sense. So this one's just spread out a little bit. But if we multiply this, it's like, I don't want to deal with pi. It's maybe easier to do by hand because all the pi's in this case end up canceling out. 2 pi times 2 is 4 pi. 5 pi times b is 5 pi b, and what I want to know is what's b. So 4 pi divided by 5 pi, cancel out the factors of pi, I have 4/5, which is, as expected, a number slightly less than 1. Not too much less than 1, because this is just expanded a little bit from 2 pi to 2.5 pi. But again, what we did is cross multiply. When you have a fraction equal to a fraction with variables in there, cross multiply. 2 pi times 2, 5 pi times b. And then to get from here to there, I just divided to get the b by itself. So just keeping in mind, just like as if that were 4x over 5x, only it's not unknown, it's 3.14. That's a factor of both the top and the bottom, approximately. So 4 pi divided by 5 pi is exactly 4/5, or 0.8. And it's fine to have decimals also. You'll see fractions a lot in those locations just because of this whole, like, relating how big is this relative to 2 pi. Fractions are a normal way to describe that sort of thing in many cases when it's less than 1. But it doesn't have to be a fraction for any reason. It can be a decimal just as well. So back to this question number 2. So the amplitude was 2. But 2 sine of 4/5 theta doesn't look exactly like that. There's one more thing we need to put into a function. I'll call it this one, g of theta. One more thing we need to insert to make it look like that. And it's a small thing. It's a negative. Yeah, sine function, if I haven't shifted it anywhere from the origin, goes up first and then down and back up. This one goes through the origin but goes down first. Now, I could say, oh, well, I've shifted it right by 5 pi over 4. You can't, horizontal shifts, like I said, are kind of a mess. If you can avoid them, do. I can also just say, ooh, flip it upside down. Make it go down first instead of up first. And doing that It's just multiplying by a factor of -1. Just like with parabolas, to make it open the other way around, makes all the positives negative and the negatives positive. So this would create that upside down. And you can check it with, if you're trying to put together a function to match a graph, especially certainly for now, you can't necessarily as easily do it on a test. I mean, you can, because you can use a graphing calculator, but you can't use like Desmos where you can kind of trace and get more information. But see if you're right, like check it out, see if it graphs the way you were expecting it to. Just realize that you don't have to use theta, you can use x, perfectly fine. But do make sure if you're going to graph something on a graphing calculator, especially if you haven't used it yet prior to a test, make sure it's in radian mode. Graphing calculators are in radian mode by default, but if you changed it for some purpose, like in a previous class when you're dealing with angles and degrees, you need to change it back, otherwise it won't know that you're talking about radians, and this would be completely not correct, because you would have done some other computation and it thinks it's 4/5 times some number of degrees. Let's see. Let's look at these graphs 3 and 4 here. So 3 and 4, without having to deal with any horizontal shifts, look like cosine functions because they have a high point, or in the case of number 4, a low point, like an upside down curve, on that y-axis, on the vertical axis, whatever letter we're calling it. So amplitude, midline, period, calculated the same way. Let me give you another minute or two to, if you didn't figure these out before, take a minute, see if you can figure these out after what we've talked about with the first two, but I will say that these are more easily related to cosine. You can write them in terms of sine curves also by doing a horizontal shift, and we'll do these after the fact, but I try to avoid horizontal shifts for trig graphs as much as possible because they're annoying. And I'm a math teacher, and if I say they're annoying, then they're annoying. Sometimes they cannot be avoided. If you don't have either the midline point or the peak on the y-axis, you have to. But many times it can be avoided. What's the period for number 3, the one on the left there? Yeah, pi, which is relative to 2 pi, exactly half. So this one might not need to do any sort of fancy formula. No, I erased the period. I have a specific example up there now. It's exactly half the period, which means we're going through our angles twice as fast, or our inputs twice as fast as our angles. So in terms of our function, we have something with a cosine of 2 theta in there. Because 2 theta means by the time I plug in an angle theta equals pi, the cosine function thinks, oh, it's 2 pi. Time to get back to where we're started. All right, so half of usual, so we have a double here. double the angle in order to make it go through all of its values twice as fast as usual. All right, so what else do I need? Let me call this h of theta to make this equation match that graph on the left. What are we missing? Yeah. Amplitude. Yeah, it's an amplitude of 3. It goes up as high as +3, down as low as -3. It's centered on the x-axis, meaning it goes equally above and below the line y = 0, x-axis. Unlike number 4. Number 4 doesn't have a midline of 0. The other 3 graphs we looked at did. What is the midline of this graph, or what's halfway between the highest and lowest points? What y value? Yeah, it goes up as high as, let's see, 6, and down as low as -2. Those are 8 units apart. So halfway between them would be 4 away from either one of those two numbers. Or, I heard it, a midline y = 2. That's 4 units above the bottom of the curve and 4 units below the top of the curve, which means the amplitude is what? If you have a piece of paper in front of you, if you draw that horizontal line y = 2, you can see the up by 4 and down by 4 more easily maybe than just staring at this on a screen and saying, how tall is this? But you can also just take the overall difference in height divided by 2. That's your amplitude. So between -2 and 6, the halfway value, add them and divide by 2, find the average, is 2. But that 2 is 4 units away from either one of them. So the period, last major ingredient of this, sometimes it's hard to see a full period, like I don't want to, like maybe it's from there to there or something. If you want to look at half a period, as long as you realize you're doing it, if you want to look, oh, well, here's the bottom of a curve and here's the top of a curve, that'd be half of a period. If you can tell how far apart those are more easily than telling the full period, as long as you realize you need to scale it, like it is a half period you're looking at, feel free to do that. Like I can say, oh, 0 to pi is bottom to top, that's half a period. So, haha, this one has a period of 2 pi, which is nice. That means I don't have to do anything fancy. No speeding up or slowing down, no alteration inside the parentheses to the angle, as long as I use a cosine function, so I'm not shifting this anywhere. I just have an amplitude of 4 and a midline of 2 to account for. Let me call this j of theta, I guess, since I've used f, g, and h. I is not a good idea. So I'd have a 4 times cosine of theta, and then to make the midline higher, just like to move the vertex of a parabola up from the origin, just a +2 at the end. So you can see that since cosine, the output from the cosine piece of this is as much as +1 or as low as -1. So you can see that the values for this are going to be between 4 + 2 and -4 + 2. So 6 and -2. Yeah?
So do you use cosine when it doesn't start at 0?
Yeah, so the 4 on this page either had their midline at the vertical axis, or the midline point at the vertical axis, like this point here is on the midline, and it's on the y-axis, this one too. So I used sine for those because that means I don't have to shift it anywhere, because that's what sine does. Sine goes through the origin if it hasn't been shifted anywhere. Even if it was moved straight up or straight down, if that midline point is the midline point on the graph, like that, is crossing the y-axis, like sine's easier. If you've got the top or bottom of a curve right on the vertical axis, right on the y-axis, you don't have to deal with horizontal shifts if you use a cosine function, because cosine has its, cosine in terms of rotation around a circle, remember, is talking about mapping the horizontal position. So cosine of 0 is going to be that positive 1, and then it turns to 0 units to the right, and then goes to negative 1, and then 0, and then back to 1. So cosine starts at a 1, dips down all the way to the negatives, and finally gets back to 1 by a full loop around. Cosine of theta, that is, if you have other numbers thrown in there, it can speed up that rotation or make it go farther away. But if you start at your maximum or your minimum, you can think of a cosine. And by minimum, there's one more thing that I need to do to this graph. What is it? Yeah?
Negative before 4.
Yeah, so I need a negative. So you can see that if I plug in cosine of 0 is 1. So this gives me negative 4 plus 2, or negative 2 for my result. Cosine reaches its, let's see, minimum, usually speaking, at pi, halfway around the circle. Cosine of pi is negative 1. So negative 1 times negative 4 would be 4 plus 2, or 6, by the time I'm at pi units. So this is upside down from a standard cosine curve. A negative takes care of that, just like this negative in front of the sine value takes care of that sine curve being upside down, starting the opposite direction from 0, if you want to think of it that way, than it would be without. So that negative flips it top to bottom. And keep in mind here, I wrote this plus 2 first because we knew that it was shifted upward. But order of operations wise, if I'm evaluating it, that plus 2 comes after the negative is taken. So that's why it's like it's upside down but moved up 2 units. Still works right. It's not like some shifted graph gets all flipped under the x-axis or something like that. Just this isn't all in parentheses negative. There is a vertical shift up 2. But the thing that's shifted up to is something that's already upside down from what we were expecting. So the order of operations is fine. You don't have to worry about like the whole opposite of everything. But if you do have accidentally, thinking test time, something that the graph is exactly upside down from how you wanted, like you need to rotate the whole thing above the axis, go ahead, put a negative in front and parentheses around everything, and that should take care of it. Sometimes messing with vertical shifts and vertical flips, if you think about it, not quite right at first, you can get yourself mixed up. But there's always a way to recover. So negative signs are very handy to work with. Anything else on these 4 functions? All right, then let's talk about the Ferris wheel stuff on the back. Got a Ferris wheel that has a 16-meter radius. Passengers board the Ferris wheel platform, from a platform that's 2 meters above the ground at the bottom of the wheel. And once everyone's boarded, the wheel rotates once every 2.5 minutes. Okay, so that's a lot of details. When you have a lot of details without a picture, it might be helpful to draw a picture. Especially if we've got a Ferris wheel and people boarding from a platform, and be as artistic as you want or not. But it might help to arrange this. But we've definitely got a circle. We're going to have people rotating around a circle. And the first thing we want to do is model the height above the ground based on how much time has gone by. And the first one is just talking about the wheel rotating once every 2.5 minutes. And then in part B, we're doing it based on a meters per second around the circumference, which we haven't exactly talked about that. Kind of hinted at it. But it's just a little conversion from what we would have previously done in part 1. Ferris wheel at a point that's 2 meters above the ground. And the radius of the Ferris wheel, whatever direction you want to measure it, is 16 meters. And we're going to rotate. It doesn't actually matter if we go this way or that way, but I'll just say we go this way. You're going to have the same pattern of heights whether you go right or left, right? So we weren't worried about the horizontal, just the height. What's the amplitude of any sine or cosine function we write going to be for this one? Any thoughts? It's the radius, yeah. If you remember the set of relationships we had on the board that we used for just computing arc lengths and distances and xy coordinates, the distance around a curve just in radius lengths is just the same as the angle measure in radians. If you want to measure it in like feet or inches, whatever sort of length units, whatever you measure the radius in, it's that radius times the angle measure in radians gives you the distance around the circumference that you've traveled. And then to find the x and y coordinates, horizontal position relative to the center of the circle, we said our cosine of theta. If it's in radius lengths, again, it's just cosine of theta, but in feet or inches or something, r times cosine of theta. And y value, or the vertical position relative to the center of the circle, is r times sine of theta. Those still all hold. But that r, if we're writing out a function, like, oh, that radius becomes our amplitude. It tells us how far above or below the center of our rotation we're going to move, which if the circle has a radius of 16 meters, I mean, it could be to the right or left also. We're talking about the height above the ground though, so we're going to be 16 units above or below the center of that circle. So that's an amplitude of 16 meters. If we're modeling our height, it's going to be measured in meters unless we wanted to do unit conversions here, which I don't. What's the midline of the graph if we're measuring height above the ground? 18, right? While we're on the Ferris wheel, we're going to go above and below the height of this point, which this point is 18 meters above the ground. So midline, 18, y equals 18. I'll just jot it down as 18 for now. So I have most of the ingredients for writing a function. It's just like well, how do I make sure that it goes around at the right speed or often enough, or however you want to phrase that. But I could write something for this f of theta equals, I can use sine or cosine, I'll just leave it blank for now. But I need to multiply it by 16, whatever function I pick, and then add 18 at the end. So if you're not sure, like, should I use cosine, should I use sine? We're modeling vertical motion here, but we're also starting at the bottom of a circle instead of starting in standard position. You can use either sine or cosine, but if you can imagine what the height pattern would go through, like imagine a picture of a graph, you can do what we did on the other side of this, use the picture to figure out which would be easier. And so on this one, we're never going to be in the negative, so I'm just going to draw it here. We're going to start at 2, have a midline. Here, I'm going to have this not to scale. Let's see. Have a midline at 18. and we're gonna go equally above and below this 18. Minimum of 2, maximum of 16 plus 18 is 34. But we're starting at 2. And by the time, how much time has gone by? Wheel rotates once every 2.5 minutes. Here's 2.5 minutes. So it's not angles I'm putting in, it's minutes. But by the time 2.5 minutes have gone by, I'm going to be back to 2 meters high. And halfway in the middle, I'd be up at 34. And halfway between those, I'd be at this 18. It's not a V shape, it's a curve. But if you see this shape and think, should I use sine or cosine? Right, it repeats. You can use either one, but it might be easiest to use cosine, because it's got that, in this case, the low point right on the y-axis. If the high or low, peak or trough of the curve is right on your y-axis, you can do a cosine function easily. You don't have to do any horizontal shifts. So I say cosine of something, just we're starting at the bottom, so make that negative, just like question number 4. And then all we have to do is figure out, well, how do I make the period? And let me not call this theta, because that makes it sound like the angle. Let me say t. I'm going to put it in time in minutes. If 2.5 minutes have gone by, I want it to go all the way around once. Well, we just dealt with the period of 2.5 pi. We just have 2.5 without the pi this time. All right? So it doesn't work out quite as nicely. There's going to be kind of a mess in here. But I can solve almost the same equation. It's just my 5 isn't going to have a pi by it. So 2 pi over b would be 5/2. I can just put 2.5 there also if I want. I'm just leaving it as 5 over 2 so that I can crisscross multiply. So we're going to get 4 pi over 5 as b. Pi over 5. And I use t as my variable, that way it looks like time instead of the angle. This way I can put in how much time has gone by, and I can see what my height is relative to the ground. So there weren't any diagrams in the question. There are a lot of numbers, a lot of descriptions about what happens when and where and relative to what. For your tests, which is in 2 weeks from today, there are diagrams in probably 2/3 of the questions. If you want a diagram in one that doesn't have one, please draw it. If you can't picture what's being described and there's a lot of numbers, whether it's a circle diagram and you're trying to make measurements around a circle to picture something, or you're trying to piece together information about a graph so that you can write a function rule for it. If you can kind of put together what it looks like, you can use some skills from different sorts of questions. Whether, sometimes one type of question is easier for you than another. If you're good at looking at a graph and writing a function, and you think it's hard to read a story problem and write a function, well, read a story problem and try to draw a graph, just a sketch of one. Because if you can draw that sketch of a graph, you can at least get the majority of what you need in order to write the function you normally do from graph questions. So, like I said, there are a lot of diagrams given, whether it's a circle diagram or a curve diagram like that, or there's a couple of triangle things also. But use all the information that you have to kind of piece it together and make it not so daunting a task. Because looking at all this, write a function for this, t = 0 is seconds, minutes. So this is time in minutes. If you wanted to use seconds, you could do that also. Instead of having 2.5, I'd have, 150? So I'd just have a whole number here, 150, and have 4 pi over 150. Or no, what am I missing? Oh, not 4 pi, 2 pi over 150. Something looks weird. Which would reduce to pi over 75, which is the same thing. Pi over 75, like related to seconds, versus 4/5 pi related to minutes. Same thing. But in any case, also much easier maybe to figure out what's going on. For how long, seconds or minutes, during a rotation is a passenger 18 meters or more above the ground? If you worked out anything related to the question, maybe in a graph, like, oh, 18. That's the middle of this. We're going to spend half our time above 18 meters and half our time below 18 meters. And we're at 18 meters for an instant as we pass it. But in terms of that 2.5 minutes all the way around, well, halfway around, even though it's not like a normal half of a period to be concerned with. It's like this, the top half, this concave down section, in reality. So half of 2.5 minutes is what, 1.25 minutes? 75 seconds would be our, yeah, I did that. Minutes and seconds was confusing me there. 75 seconds or 1.25 minutes would be how long you're above that. Same as how long are you below it, because it is that midline. If it was a different number, it would be hard to answer. We'd have to know some other facts, do some more computations. But that's actually just asking how long is it above the midline versus how long is it below the midline. And since it's the midline, it's half and half. So there's something else that reminded me of. Oh, concave down. So we talked about concavity before, but just a fact about these graphs that's made, if you're trying to sketch them and aren't having much success at making them look like the ones that you see in graphs, when you're above the midline, you're going to be concave down. When you're below the midline, you're going to be concave up. So just if your graph looks too pointy or isn't curving in the right spaces, think about where the midline is when you're sketching it, and think about concave down or concave up. It's always curved toward the midline. And right at the midline is where those inflection points are, the changes in curvature. All right, so last thing on this one. And this is just a little bit of an extension beyond what we talked about before. So suppose that instead of talking about it rotates once every 2.5 minutes, what if this says we know that the speed of a person around the circumference in meters per second, 1/2 meter per second around the circumference of this Ferris wheel? We want to know how long does it take the Ferris wheel to make a full rotation if it's going at that speed? And then what would be the equivalent speed in radians per second instead of meters per second? Because we have done some questions with radians per second before. And then write a function for that. So think about that for a minute. And this will probably involve a calculator to get a good sense of what sort of number you have. It's some not easy to parse numbers here. Swap these boards. So any thoughts on how to answer this first part? Given this 0.5 meter per second, how long does it take to go all the way around? Any thoughts on like maybe some place to start? Okay. Yeah, Christian? All right, so it finds the circumference. So circumference is pi times diameter, yeah? I can write that. So in this case, that would be 32 pi? Or, I know I have to travel 32 pi or about 90 something meters. This is in meters. 100.53, okay. Approximately. So if I want to know how long it takes in seconds to go all the way around, I have a distance and I have a speed. If I need the time,
Divide by 0.5.
yeah, and just divide. So distance equals rate times time. So if I have a distance, and you can save the rounding for the end if you want, but here's our distance. If I divide by my rate, I'm going to get my time. So like, you know, with more normal numbers, you have to go 150 miles. If you're going 40 miles an hour, how long will it take you? Oh, just 150 divided by 40. Same sort of thing, only it's 32 pi divided by 0.5, which will be about 201 seconds. So time here is about, rounded to the nearest second, 201 seconds. It's still approximate, but rounded to the nearest second, it's 201 seconds to go all the way around. A little over 3 minutes, right? So let's leave it in seconds. If I wanted to know what is the speed in radians per second? Speed in like meters per second is 0.5 meter per second, which leads to taking approximately 201 seconds to go all the way around. So if I want radians per second, what computation can I do? If I want meters per second, that's just a number of meters divided by a number of seconds, right? So this number of meters divided by a number of seconds gives me meters per second. If I want radians per second, well, this is how long it takes to go all the way around. All the way around in radians is how much?
2 pi.
2 pi. So 2 pi divided by that. So 2 pi radians divided by approximately 201 seconds. About 0.03 or something.
Yes.
So like it's about pi over 100. So whatever, not nice numbers in this problem, but 2 pi radians in about 201 seconds. Now, if we left that in terms of pi, we could see it as a fraction of pi or something, but just looking at this, it's about 0.03, we'll just leave it as that, radians per second. So this is our speed. If I want to write a function where time was the input, and I had this speed, 0.03 radians per second, instead of, what did we have last time? For part A, it was 2.5 minutes. So 2.5 minutes to go all the way around. That's, let's see, 2.5 minutes, or whatever. If we want to change that and compare how much these speeds are different from one another, we can. But we have a speed in radians per second. Oh, wait. It's down here, so we already have a function. We're still gonna have something like that, but just with a different sort of input, because we've got a different speed. So let's say, and I'll call this g of t, where we've got a new speed of 0.03 radians per second. Still gonna have this negative 16 cosine of something plus 18. But I can convert linear speed to angular speed. The thing is, it takes 201 seconds to go all the way around. In terms of answering this question, like this 201 seconds is the number we're using. That's kind of useful because between 0 and 201 on my axis, that's where it's going to go through 0 to 201 time, seconds. It's going to go through its whole period. So zero to 201. So that means if I put 201 here, and you can see where this is going to relate. If I try to solve for that b, notice what I'm doing. 2 pi divided by 201. That's the exact same thing we just did. This speed here that we just calculated is the same as this b that we had there. So I'm going to call it 0.03 t. But those sorts of speeds, angular speed, in radians per second, radians per whatever time unit you happen to be using, will allow you to use an input of time with that speed just multiplied on. It's not like a magical other formula. It's still the same relationship between period and that coefficient. But if you see something like sine of 2 theta or sine of 2t or sine of 5x or whatever, you can think of those multipliers on there as a speed. The larger it is, the faster it goes through its set of values. This one goes through very slowly. We've got this 0.03. It takes 200 something seconds for this to get all the way back to the beginning. So thinking about like 0 to 200 and something on the axis, it's time, it's not radians anymore. But that's a lot more than 2 pi is 6 point something. This is 200 and something. So regardless of, it's different units, but thinking about the sizes of the numbers that we're using with this such a small coefficient or a low speed, that's going to make the numbers along the x-axis a lot bigger, or the horizontal axis, a lot bigger for us to go through one full period. All right, so in any case, that's that with sine and cosine modeling. And by the way, this one was modeling vertical position, but just because of where we started, it was easier to use a cosine function for that because we didn't start at the horizontal 3 o'clock position. We started at a vertical, whether it's thinking clocks, 6 o'clock or 12 o'clock position or something like that. You can use a cosine function to model that without having to deal with horizontal shifts that way. All right, so let's take a look at tangent function. So the tangent function is related to sines and cosines, but I want to point out this is 7 investigation 8. You can see this. If I had these coordinate points on these circles, notice that the radii on these circles isn't labeled, but if I had coordinate points, I could find the radius, right? Because, I've got x and y points, so I can figure out how far that is by Pythagorean theorem / distance formula. We talked about that back in chapter, I don't know, however long ago not with multiple concentric circles, but just how far is a point from another point, or how far is a point from the origin, very specific other point. You can use Pythagorean theorem or distance formula to figure that out. Now, that means that I could find the sine and the cosine of this angle theta, because I can figure out the radius even though it wasn't given to me. So I could do that, like, do I still have it written, or have I since erased it? Probably since erased it. X equals r cosine theta and y equals r sine theta. I can still use those relationships and solve for, write the x and y coordinates in terms of sines and cosines. I don't really want to find theta, but I could talk about those relationships in terms of whatever this angle theta is. But if you can see, this is a straight line here. The relationship between x and y in those 3 points, regardless of how far apart they are, whether these were much smaller or much bigger circles, since these x, y points are all on this one straight line, the slope between any two of them, including between the origin and any one of them, is going to be the same number every time. And that slope, related to what we're talking about here, is the relationship between x and y, obviously. And I'm going to just talk relative to the origin, because if you have to find the slope between 2 points and you have an option of one with a lot of zeros in it, that's a lot easier. And that's what this worksheet does on the next page. But I'm just, so I can draw on it. So radius of the circle, you know, I could use x and y distances, make a little right triangle, find the radius from knowing the x and y. But I also know that, let's see, we just said x is r cosine of theta, y is r times sine of theta, and the slope, which the slope between x, y, and 0, 0, is the same for all of those x, y points. It doesn't matter which one I pick, because they're all in a same straight line at the same angle. They'd all be like change in y over change in x, which obviously is just the same as y over x. So since it's just the same as y over x, I could also call that sine of theta over cosine of theta. Eliminate the r's, it's the same thing on the top and the bottom. Just kind of like when we were doing some, cancel out the pi's over there. Same factor on the top and the bottom, whether we know it or don't know it. And this ratio, sine divided by cosine of the same angle, which is also the same as the y coordinate divided by the x coordinate of a terminal point for some, or a point on the terminal ray of an angle for some circle, y divided by x, or sine divided by cosine, is known as tangent of that angle. So the tangent function of an angle, if we draw that angle into a circle in standard position, all the tangent function is the slope of that terminal side. So I can see right here, this is a smallish positive slope, like less than 1, because the x values are smaller than the y, or the y values are smaller than the x values. So like 8/15 or 6.4 over 12. It's almost a half, but not quite. It's a little bit more than a half, so like 0.5 something. If I had points that were closer down here, they have lower positive slopes. And as I rotate and make larger angles through the first quadrant, I get higher and higher positive slopes. So this tangent function, if I were to think about what sort of values does the tangent function have, it's not like sine and cosine directly. It's related to a ratio of the two of them. One gets bigger, the other gets smaller. That makes a whole weird set of values. But if you can just picture what happens to the slope of this interesting side of the angle as we go around. Well, if I were actually at 0 degree angle, 0 radian angle, that'd be a horizontal line, slope 0, right? And as I move through the first quadrant towards pi over 2, my angle gets steeper and steeper, or that terminal side slope gets higher and higher. First slowly, and then more rapidly, but I don't actually have a slope number to say for if I'm at this, 90 degrees pi over 2, right? Slope over vertical line is undefined, but just before that, I've got an extremely high positive number for slope, right? And the closer I get to vertical, the larger that slope gets, like 100, a million, a billion, whatever. I can get closer and closer and closer, but the second I hit exactly vertical, undefined fraction. So we have this vertical asymptote there. I can get closer and closer. This y value in this graph indicating the slope of the value. So this is y equals tangent of theta, or y equals the slope of the terminal side, the interesting side of this angle that's in standard position. But I do have more values. I can continue on past 90 degrees, right? Past 90 degrees though, if I'm on this other side, and there's pictures of it in here. If I'm in the second quadrant, that terminal side has a negatively sloped line, right? This line from left to right is going down. If it's extremely close to that vertical line, it's extremely negative. But as I continue on towards pi radians, that slope's getting closer and closer to 0 again. From a negative, like 1 halfway through, finally down to like 0. Not like 0, exactly 0, by the time I'm at pi. And it continues on past that. It's going to be positive if I go on into the third quadrant, and so on. So we'll talk more about tangent function on Thursday, but I hope that gets you a little bit of a start on the 7.8 lesson that's due tonight. Your 7.8 homework isn't due till Thursday. Take a look at it. We'll go through some more of this investigation on Thursday, along with some right triangle stuff. All right, I will see you then.